I just realized I don't have your bio, so I guess I'm gonna try my best. Or if you have a quick bio, feel free to send that to me. Um,
Sure thing. I can send one. And the introduction can be very brief. It's okay, but I'll
okay,
try.
it's up to you. I can certainly put together a very brief introduction, but
I mean, I can send. Yeah, I can send one I've been using really quick via email. Hang on.
yeah, that would be great. Thank you.
Yeah.
Huh?
All right. Um, we can try to get started. Um, I that was probably a bad idea since my email may not be on time. Um, cool. Thanks. Um, Feel free to share your slides again. I'm not seeing the slides. I'm seeing the empty screen. I guess I learned that this is California. That's kind of interesting about um, macOS. Anyway, cool. I'm very excited to have Downey as our speaker today, and he's a senior director of semantic scholar research at the Allen Institute for AI, AI2, and a professor of computer science at Northwestern University. And his research focuses on natural language processing with an emphasis on AI systems that support scientific discovery. At AI2, he helps lead the Asta project, which we will learn about. I've learned about this. I tried various parts of Asta a little bit myself. It's a very cool project, and his publications have received paper awards at ACL, MLP, EJK, and AKBC. And maybe a little backstory about this. I think Doug helped organize a workshop at NACO last year that kind of inspired a lot of why we are having this online seminar this right now. So it's great to have Doug here with us. And Doug, please get started.
All right. Yeah. Thanks very much, Chin Hao, and it's great to be here speaking with you folks. Yeah, I'm going to talk about the ASTA system, which is a large project at the Allen Institute for AI aimed at accelerating science. So we'll start with a schematic, simplified illustration of the scientific workflow. So scientists start by searching for and discovering previous work. They invest in reading and understanding some of that, and that allows them to generate hypotheses. They can then plan and execute experiments to test those hypotheses, analyze the data that comes back, and finally write and promote their work. So the ASTA project is aimed at building an assistant that can help with this entire workflow. And we want this assistant to not just chat with you, but also use all of your tools and data. So when you get experimental data back, or you access the literature, write notes, code, or use tools and so on, Asta should be able to help you with that. Should be able to execute the same tools you can use and look at the same data. So this is the vision. I think we're still in relatively early days with this vision, but we have released a variety of tools, and I'll talk about some of these. This is our set of releases over the past year. Um, and we've gotten a fair amount of usage of these tools, so more than 200,000 interactions so far. And I'll talk a little bit later in the talk about how we're using some of this interaction data to help build benchmarks that we're hoping the field can use to improve tools like these. Okay, so let me start by let me jump into showing you some of the capabilities that are currently in Asta. So here are some demos of some of the tools. I'll start with this Find Papers tool. So this is a search engine for papers, but aimed at helping you find hard to find papers. So you can ask complex queries like, oh, I remember there was a paper where Bert outperformed Roberta on some tasks. Like, can you find it? And Paper Finder is designed to handle those more complex kinds of queries. So here's an example. What if I were asking for non-summarization papers by Marilla Lapata? So Marilla Lapata wrote a bunch of summarization ones, but I want the other ones. This is kind of a hard query to do with conventional tools, but you can do it with Asta Find Papers. So Asta takes your query, analyzes it, and eventually returns this result set, giving you, in fact, a bunch of non-summarization papers by Marilla Lapata. Then you can go over to the right-hand channel if you want and select the somewhat relevant ones, and that'll give you the ones that match the Marilla Lapata part, but not the non-summarization part. So this is the paper finder, and it's a public tool. I encourage you to try to use it. Moving forward, AST also has a summarized literature tool. So this is something that returns not a list of papers, but instead a long form report, similar to OpenAI research, deep research. For those of you familiar with that, so here's what that looks like. You could search for something like what's the Van Ebers technique for calibration, and Asta thinks about your query for a while, sends it off to some indices, and starts writing a report. This takes a while, so after a couple of minutes, you get this report. It's broken into sections outlining the key themes of the answer. You can dig into these sections and get individual claims. Each of those claims is supported by a citation. When you click on a citation, you get information about the paper and excerpts from the paper that support the citation, and then you can actually dive into the paper and see those excerpts in context. So that's Asta summarized literature. And Asta analyzed data is not quite public yet, but will be soon. This is a tool that helps you analyze data sets. So here's what that looks like.
Scientist. I collected participant level responses in a behavioral study evaluating how humans detect lies in conversations.
So this has audio associated with it, but I'll just speak to it. So what we're doing here is uploading a data set and then describing it. So this is a data set that captures participant level responses in a behavioral study, evaluating how humans detect lies. And then you can ask a question about it. So this user is going to ask the question of, do female participants switch to AI advice less frequently than male ones in the AI accuracy treatment in this data set? So Asta takes your data set and writes code to analyze it, and ends up producing this contingency table that leads to the conclusion, yes, in fact, there is a significant difference in AI switching behavior between male and female participants. Then you could say, can you show me that graphically? And it gives you this bar chart visualizing the results. Okay, so that is Asta analyzed data. It is not yet public, but will be soon. So for Find Papers and Summarized Literature, I'd encourage you to give these tools a shot. So they are public tools. They're available on asta.allenai.org. Please just give those a try, and tell us what you think. There's feedback links in the tools. So encourage you to try those things. All right, so that's a that's a sort of whirlwind tour of some of the tools that are available in Asta and the goals of the program. For the rest of the talk, I'm going to talk about a handful of things. So you may be wondering, there are already similar tools to what Asta is offering out there, on the web, and you might be wondering, how does Asta compare to those? Or, in general, how can we tell how good any of these tools are? So that evaluation challenge is what led us to build AstaBench, which is, we think, the first holistic benchmark for evaluating how good scientific assistants are. So I'll describe that at a high level, and then I want to dive into a handful of details for each of these projects. So I'm going to tell you exactly how the ASTA summarized literature system works and some early experience we've had with that tool. And then I'm going to talk about how we evaluate that. So this is part of AstaBench that's designed to evaluate the summarized literature tool. That's a data set we call Scholar QA CS2, where CS is for computer science. All right, so this is an outline for the talk. Oh, by the way, there's a whole bunch of future work to do. So along the way, I'm going to outline 4 open challenges that I think are important for the field to tackle in AI for science. All right, so let's start with AstaBench. This is work led by Jonathan Bragg. So there are already a number of benchmarks for evaluating LLMs. Why do we need another one? Well, when we looked across the landscape, trying to build or trying to evaluate scientific assistants, we realized there's a set of principles that we think are important for evaluating scientific assistants that aren't available in existing benchmarks. So what those are is, first, we want the tasks in our benchmark to represent real world usage. So tasks like those in Asta, the kinds of tools we're putting in the hands of real human scientists, we want to evaluate those kinds of experiences, not more artificial things. We also want to use real world tools. So for example, accessing the literature requires a strong search engine that has a large number of papers indexed in order to be realistic. And that's one of the tools that we ended up releasing with the AstaBench benchmark. It uses the same production search indices that Asta uses, that Semantic Scholar uses. And that, we think, is a virtue of this benchmark. The tools are sort of realistic production grade tools. It's really important to control for confounders. So in particular, cost. It's been well established that agents can be better if they just spend more compute at test time. So even simple things like just trying the same query multiple times and taking a majority vote can reliably improve performance. So if you don't account for cost, you can be misled into thinking that a method that's actually inferior is performing better, but it's doing so just by expending more cost. So controlling for those confounders, cost, and also the tools was important. There have been exciting general agents that have emerged recently. So things like small agents or the React framework, agents that can take just a description of a task and then run on it. We wanted our benchmark to be easy for evaluating those types of agents. And finally, we wanted to supply a set of strong agent baselines. So these are the 5 criteria that led us to create a new benchmark. I won't go into the details of this table, but what this table is basically saying is, if you look across a large number of benchmarks from the recent literature, in general, they didn't have all of these criteria that we were looking for. Okay, so here are the very high level results. I'm going to show a number of graphs like this. Understanding where all of the systems sort of fall in these graphs is not what I'm trying to get across. There's like a lot of information in these graphs. If you want to see them, they're in the paper and in the blog post. I'm just trying to communicate a handful of high level points. What you'll see here is that Asta is the best of the various systems we evaluated in this chart. This chart's comparing a couple of different generic agent frameworks, React and small agents, with a bunch of different backbone LLM models. And Asta performs the best, but it's also the most expensive. And none of the systems perform especially well. So that's kind of the most important headline result. The very best performance is a shade above 0.5, and it's at relatively high expense. So there's still a lot of work to do. All right, so I'm going to briefly say a little bit more about what's in this benchmark. The tasks, there are 11 of them, fall into 4 different categories: literature understanding, code and execution, data analysis, and then end-to-end discovery. So let me say a little bit more about the individual tasks in this benchmark. Several of them come from previous work. A handful are newly introduced with AstaBench. So I showed you the find papers capability that does search, enter a text query, get back a ranked list of papers. We grabbed a couple of, or took one benchmark from previous work for that, and also created our own. So we found that there weren't good benchmarks for that sort of really challenging case where there might be metadata queries and a diversity of different types of semantics that Ask to Find Papers is designed to tackle. So we built a new benchmark to get those questions. We also have a deep research benchmark. So this is where you produce a report, like Ask to Summarize Literature. There are a large number of benchmarks that have recently appeared for this task, but when we set out to do this work, there weren't as many. So we built our own, and I'll say more about this later. This is based on real user queries and a new set of evals that I'll talk about later on in the talk. We also grabbed a multiple choice benchmark that requires digging into the papers. This is from previous work, and a table generation benchmark. This is where you have to produce a literature review table. You get a list of papers and an information need, and you try to build a table where each row is a paper and the columns are shared aspects that allow you to compare and contrast the papers to address the information need. And this is a benchmark from previous work. Okay, so those are the literature understanding benchmarks. And really quick, here are the high level results. We, again, the green triangle is the Asta system. It performs the best, but it's more expensive than a bunch of the other systems. And, none of these systems are all that good. So literature understanding, I think these tools are useful today, but there's clearly a lot of room for improvement. And there's a reason why you should take all of this graph with a grain of salt. And I'll come back to that later. I think evaluation is still quite tough in this domain. Okay, so briefly, scientists, especially in the computer science domain, write a lot of code and execute it in order to do science. So we have 3 benchmarks aimed to test that. The super expert benchmark gives you a repo and asks you to run a task on it. So given that repo, you produce a Jupyter notebook that carries out the task. Core Bench Hard came from previous work, involves reproducing particular results from previous work, and DS1000 is a data science benchmark aimed at answering Stack Overflow questions that have been modified to avoid contamination, and tests NumPy and Panda usage skills. So just one quick result from the code and execution benchmarks. This was quite interesting on Super Expert. So GPT-5 was a late addition to our analyses, came out not too long ago, and really improved the performance of the general React baseline. So none of the systems do too well in Super Expert, but certainly the ones powered by GPT-5 do by far the best. And those those really changed the picture here. Before GPT-5, the highest score on this benchmark was 0.25. So we thought this was interesting. At relatively low cost, this general agent framework React with GPT-5 did quite well. Previously, the Asta system was providing a boost over React using older LLMs. With GPT-5, though, the generic agents were actually doing the best. This is an interesting contrast, though, the sort of overall poor performance on this task compared to, headline grabbing results in like contest programming. So it seems like this real world task of getting a maybe not super well documented repo and reproducing an analysis is a tough problem, and maybe harder than some of the contest programming where LLMs do incredibly well. Okay, so data analysis, right? Various scientists end up analyzing data sets in their work. You saw the Asta tool for this in action, and this benchmark is similar to that kind of use case. You're given a data set and a question like, oh, is this hypothesis true in this data set? And your task is to go out and determine whether.
Can I ask a question on the previous
Yes,
slide?
sorry, go ahead, please.
I guess like my understanding is that this is a React agent that you wrote and then you put GPT-5 as the underlying model. What about using Cloud Code or Codex directly, like which I guess
So
is
yeah, we
common?
haven't on this data set benchmarked or yeah, the other ones I've mentioned. We haven't benchmarked coding agents like Codex or Claude Code. Um, and in general, so the case where we have compared against commercial tools is in summarization, and I'll talk about that later in the talk. Um, and the coding agents, I think we just sort of haven't gotten to those for these tasks. It's interesting that, the reason why I'm focusing on React and small agents is because they're the systems that can address all the tasks, in the same way Asta can. So, for something like OpenAI Deep Research, which we'll evaluate against later, it can do this sort of report writing task, but doesn't natively do these other tasks. So we focused in this evaluation on agents that could do everything in the evaluation I'm showing you right now. And you're right that we should try the coding agents on tasks like this. I don't have those numbers today, but I will have numbers against state-of-the-art summarization systems later in the talk. Great question. Thank you. Moving forward, so here's a set of results, and I won't belabor these, but on the data analysis benchmark, none of the systems do especially well in this task. It's worth noting that these are hard tasks, so they may not be representative of user workloads, and we'd actually like to find more representative ones after we release the tool and know how people are using it. Finally, end-to-end research gives you a research task like, I'd like to know if I discover prompts for large language models, can they improve small models? This is a maybe interesting research question. It'd be nice to know what the answer is. And this is the task the agents are supposed to do. They're given as input a large procedure that they're supposed to follow in order to answer the question. And also the reason why we do this is there's a rubric associated with each of the steps. So that way we can unambiguously or, relatively unambiguously address and evaluate how well the agent carries out the task. So these agents think for 10 or 20 minutes. That's even after we tend to radically simplify these tasks in terms of like the size of the data. So we're not getting back bona fide conclusions over real world data sets, but instead testing whether the system can carry out those steps. Then the system produces a paper, code, and data sets. As I mentioned, there's this large rubric that also is output. These things are output by a combination of LLMs producing the first draft and then humans editing what that output is. And there are 80 tasks of this type. And then we evaluate how good the agents are. And here's what we see here. So the Asta systems do pretty well, but they're like much more expensive than the other ones. So clearly there's a sort of cost accuracy trade-off here. The vertical axis kind of overstates the level of quality. So this is the accuracy in carrying out a single experiment, which gets close to 0.7. But of course, to do an investigation, you might need to do 10 experiments in order to produce, a clear and correct answer. And there, errors tend to compound, and these systems are not nearly as good. Okay, so that's an overview of the AstaBench data set. High-level points. First, overall performance is not that good. I think there's enormous room for improvement in assisting scientists to do their work. So I don't think this is a solved problem. There are several impressive results. You hear about them sometimes in the news, but in general, there's a lot of work to do to solve this problem. This is the thing I mentioned in response to the question about coding agents. So commercial tools can only do a fraction of the tasks. That's why I wasn't showing them. Talk about some commercial tools for summarization a little bit later. In general, we saw the Asta science optimized agents were better than general purpose, and this may not have come across super clearly, but basically, the Asta systems are for the most part specially designed prompting workflows that are designed to solve these scientific problems. And I'll say more about the summarized literature one in a second. And what we found is that investing in those pipelines tends to improve performance over general purpose agents. Although the gap is not always huge, and in fact sometimes not present as we saw with the like on the super expert data set. This fourth point was a little bit surprising. So if you use a more expensive language model, you can actually sometimes lower task execution cost. So, and this is because these agents, the number of inference steps they take is like a free variable that they can choose. And sometimes the lower cost agents make poor choices in that regard, or they get stuck in loops. And so they end up spending more, despite the fact that they're lower cost per token. And then finally, we saw GPT-5 really improve performance in certain cases, but actually didn't in many cases if you plug them in to the Asta systems. The Asta systems didn't necessarily do better with GPT-5 than they did with earlier models. All right, AstaBench is freely available, and it includes things like production grade tools. You can get an API to query our search index that's free. It's hard to build one of those, and so we think that's a particular value of our data set. I encourage you to give this a try. All this stuff's publicly available. All right, so moving forward, that's brief overview of Asta and AstaBench. Now I want to dive into a handful of details. Talking about the Asta summarized literature system next. So let me tell you exactly how that works. I think you understand the problem setting, right? You're given a complex question, you produce a report. The three folks on the slide here were the leads of this project. There was a larger team also involved. Here's how the system works. You get in a query and we send it to a couple of indexes. One is a sparse and dense Vespa index. The dense embeddings we found worked best after quite a bit of experimentation were mixed spread embeddings. And that Vespa index covers the full text of 12 million papers. We also do an abstract search of Semantic Scholars, larger index that doesn't contain full text, just abstracts. There are 108 million of those. We then hand those retrieved snippets off to an off-the-shelf re-ranker and try to get the good ones. That's a cross-encoder model that does the re-ranking. Then this starts getting expensive. We hand this stuff off to frontier LLMs. We're using Claude 4 in production. We filter those snippets down to the most relevant ones, choose the exact quotes from within them. Original snippets might be 500 words. The exact quotes that are relevant to the query are often shorter. Then we cluster those quotes into themes. Those are the sections of the result report that you saw a moment ago, and then finally write the report one theme at a time. This isn't a radically novel pipeline. There are similar things in the literature, but it's one that we found works well after we experimented. So here's a little bit about what we're seeing from users. People have been using it relatively steadily. An interesting fact about this graph is that the returning users, that's people who come back on multiple distinct days, actually make up a substantial fraction of the active users who use the tool at least twice. So 60% of the folks who use the tool twice are coming back on multiple days, which we thought was encouraging. Seems like people are getting use out of this and using it to do actual work. We gather feedback in the tool, and most of it's positive. have to take this with kind of a grain of salt. It's only certain people that click those thumbs, but in general, it's been positive feedback. Here's a simple but I think fun graph that shows which sections of the answer users tend to expand. And you can see it sort of trails off as you get deeper into the report. But interestingly, the first section is not the most expanded. That's because every report starts with a background section, and only certain users, actually want background. Some of them want to jump right into the answer. So that's what we see there. Here's a more complex graph showing how different kinds of users tend to enter different kinds of queries. So users that use the tool a lot, what we're calling experienced users using it more than 10 times, tend to enter fewer broad topic queries like, what is deep learning? And they instead look into, more precise definitions or causal or relational information. We're kind of just now completing our analysis of user behavior in this tool. And we're looking to publish an analysis, including things like what I just showed, and also the user behavior data. So this is a pretty large set of queries and users, and a variety of actions they did in the tool. And we'll be releasing this for the community to use to try to study how people are using these systems. These, by the way, are folks who explicitly opted into sharing their data. A data set we have released is a compendium of the citations we've made in our reports. So in general, the field of AI could be doing a better job of crediting the authors whose text is powering the amazing feats of LLMs. When you have a retrieval augmented generation system like Asta Summarize Papers, you can do better, right? You actually cite sources in those reports, and so that's good. Existing deep research systems do that. What we wanted to do is go a step further and actually record those citations and release those so people could know, across all the questions that we're getting, where people have opted in to share data, how many papers are being cited, how many times. So that's what this data set is. About 5 million citations. You can see on this slide the top 5 most cited papers. Those are kind of usual suspects from deep learning and NLP. And the goal is, that we give credit to the authors, but also hopefully provide a helpful data set that people can use to study how AI systems are citing things. One question we probed with this data set was, are we making the rich get richer? So this is a concern with AI tools, that they'll focus attention on the high profile papers and end up like crowding out important other work that has important findings, but is not quite as popular. In our data, we're actually finding that the opposite is true. So if you look at the top 10 most cited papers by Asta reports, 34% of all citations go to that top 10%, whereas if you look across a set of papers published in 2025, 63% of those citations go to their top 10% of papers. And it gets even more extreme as you go up into the higher ranked papers. So we weren't really expecting this, but this is what we found. Is Asta is actually less skewed toward the most popular papers than human authors are. Okay, so that's what we found with the summarized literature system. And now for the last section of the talk, I was going to talk about this analysis we have, this data set we have for evaluating Scholar QA, and then I'll get into these open challenges. This data set work was led by Jenna Huang. Okay, so the way our evaluation works at the 10,000-foot level is you get it in the user query and a system report, output by a system we're trying to evaluate, and we output 4 metrics. The answer coverage measures whether the answer in fact covers all the necessary ingredients. Answer relevance evaluates whether all of the report is actually relevant to the question. Citation recall is a fraction of claims that are fully supported. So that is, grab a claim, are there actually adequate citations and excerpts from those citations to support the citation, or sorry, the claim. And then lastly, citation precision is, the flip side of that. If you grab a random citation, does it in fact support the claim it's attached to? So these are our 4 metrics. We use LLM as judge. I won't sort of belabor the details on this, but the answer coverage question is a bit nuanced and where we did a bit more work. So it's a little hard to define what the necessary points are for a given randomly drawn question. The way we defined that was we used an analogy to the Trek competitions for information retrieval, and we used a pool-based approach. So we query a bunch of existing state-of-the-art systems, see what they cover, and the union of that with selection by an LLM judge is what we call the correct ingredients. So we get all of these model reports from state-of-the-art systems. We extract their key ingredients using an LLM. We then use an LLM judge to choose which of those, actually cluster those together, and then choose which of those clusters are most important. And then we're left with must-have and nice-to-have ingredients. And this rubric then is what we evaluate on. We did this for 100 real user queries and have shared the rubrics. So then once we have this rubric and you give a new report at test time, we use an LLM judge to say, which of these ingredients are actually covered in the output report. All right, so that's answer coverage. Answer relevance is an LLM judge approach that just goes through each paragraph and rates it as relevant to the result or not. Citation recall looks at each claim and says, is it supported by the collection of citations that are present? We do lean heavily on the excerpts that many systems provide from the cited paper that's supposed to support the claim. And I'll say a tiny bit more about that in a second. Citation precision goes through each citation and says, does it support, at least in part, the claim it's attached to? All right, so as promised, here are some results that do use a variety of state-of-the-art commercial systems. So you're seeing our four measures and then the overall average. So Asta summarized literature ends up winning here, which we weren't actually necessarily expecting. But it's important to note exactly how it's winning. So if you look at the top 3 systems in this overall ranking, they're doing quite well on citations, actually not always the best in the first 2 columns, coverage and relevance. And there, OpenAI Deep Research and Perplexity Sonar Deep Research, these commercial systems do actually quite well in those first 2 columns, but they do less well in our citation measures, and that ends up making the difference. So I wanted to give you a handful of examples of kind of what's going on here, so you can see what we're measuring. I actually, before I do that though, notice the top 3 are all systems that are designed for science, and I think it's part of our design of both our system and our evaluation. The systems should stick very closely to what has been published in previous work, and that's probably why you're seeing the performance trends you are here. Let me go into some examples that might illustrate this more. So here's a case where the citations don't have enough detail to support the claim. So what OpenAI Deep Research outputs is this text at the top: improving training data diversity, refining model training with ethical and factual objectives can reduce risks of hallucination and bias. And it cites this source that I've quoted below and provides this excerpt. So notice the excerpt doesn't talk about any of those proposed solutions for hallucination bias. It instead just talks about the problem. And in fact, that's true of the containing document as well. It talks about this problem, doesn't propose these particular solutions. So the statement that OpenAI Deep Research is making here may be true, but it's not actually supported by the source document and certainly not by the excerpt. So So this is the kind of mistake that we often see that's contributing to those lower scores. We also see a lot of problems like this, so partially supported claims. So I won't go into this one in as much detail, but this output by OpenAI Deep Research is talking about a couple of models and a couple of training techniques or learning techniques. And the cited document and excerpt talks about only a fraction of it. So it talks about one of the models and one of the learning techniques, but not all of them. So we see a lot of this sort of like partial coverage as well. Again, what OpenAI Deep Research is saying may be true, but what the citation measures are targeting is do the excerpts actually support the claim? Okay, so I mentioned before that you should take our evaluations with a grain of salt. And so here's this kind of disclaimer slide talking about how we're really still, I think, we're working on this in a lot of ways. So these systems are hard to evaluate. And here's kind of the general trends that we're seeing. If we put two reports in front of a human judge and we ask, which of these do you like? And then we provide the same comparison with our AstaBench score. How often do those two judgments agree? So the human side by side and the sort of relative score output by AstaBench, that's what we're looking at on this slide. And we see that for overall system ranking, like you take 100 queries and rank a bunch of systems, we get relatively high agreement. So these are decent Kendall taus. Also at the instance level, so how good is this report versus this one? We do pretty well on citation precision and recall. So those are, at least decent agreement. However, we don't get high agreement at the instance level for measures like coverage and relevance, and then also the overall. So for a given pair of reports, our scores are not actually super high agreeing with human judgments of those reports if you look at coverage and relevance and also overall. So part of the reason we think is that coverage and relevance especially are actually quite subjective. So what an answer should cover, which is what both of those measures are targeting, really depends on the user's need and their background, like what they need to learn. And that can be very different for different users, and our system, our evaluation, is making one set of assumptions. It seems really important for future evaluations to specify more about the user context and evaluate in that setting. And there's been some previous work calling out that general need, but we think it's especially important in this setting. Okay, let me say a handful of things about stuff we're not evaluating. So we have these 4 measures. One of the things we're not addressing is whether systems are citing the best previous work. So there's in particular this issue of citation following. So here's a phrase: BERT is based on the encoder of the transformer model, which is proven to obtain state-of-the-art accuracy across a broad range of NLP applications. So this sentence is from Huang et al. 2020. And if we were consuming that in a RAG-based pipeline, naively, we might just summarize that as this sentence. So BERT showed how a transformer could power this. And so this is a good paraphrase, but who would we attribute this to? We'd attribute it to Huang et al. 2020, right? So that's where the text came from. But the problem is an NLP audience expects to see Devlin et al. Cited here, right? In the same way Huang did. So choosing the canonical citation that is actually the original source of a claim is something that our Asta system doesn't always do, and we're not evaluating this at all. So this, I think, is a nuance that needs to be included in the evaluation. A more significant one that we're not evaluating is, for lack of a better phrase, scientific understanding. So I want to illustrate something that can go wrong here. Here's a query. Has anyone scaled topic models to hundreds of thousands of topics? Does it improve held out likelihood? This is our system, Asta. It outputs these 2 blocks of text and says there are conflicting results. So some research says it helps. Other research says it doesn't. But this is actually not a good description of the situation, because if you dig into these results, what you'll see is going on is that these cases where it doesn't help are from 2010 and earlier. They're older methods. They use smaller data sets. And that's where more topics may not held out likelihood. These other methods are from 2015 and later, and were designed to actually scale to large numbers of topics. And there, it does improve held out likelihood. So ASTA doesn't describe this difference at all. It just says there's a conflict. So this is a major problem, and we see this a lot in our tools, actually, that just sort of the level of understanding of problem settings, of experimental results and experiment setups just isn't that present in these tools. So we need evaluations that tackle this. All right, so all of this put together, all those sort of caveats I've been issuing, leads to the first open challenge, which is how do we comprehensively and accurately evaluate long-form QA systems? We think our data set is helpful. I would still encourage you to use it, but I think there's still a ton of work to be done to make these evaluations better. Okay, so briefly, and I don't have too much more to cover, but I do want to take this brief detour to talk about reasoning capabilities. So, LLMs are amazing reasoners in many cases. They can do contest math, way better than I ever could. So what's going on? Like, why are we seeing this, gaps in scientific understanding that I just showed you in the previous slide? So I want to illustrate something, and I'm going to do this using the game of chess. So hopefully, you don't have to be a chess, aficionado to understand this, but it is helpful if you know the rules. But even if you don't, hopefully you get something out of this. So here's a chess game. Here's some text notating 8 moves for each side of a chess game. If you gave just that text to a human without a board in front of them and asked, what's the best next move for white? That's a really hard question. So, I play chess as a hobby. I can't track the game state for 8 moves for each side and answer a question like this, like not even really close. But if you give this question, just this text to O3 medium, it in fact comes up with exactly the right answer. So it tells you the right next move and exactly why white has, a major advantage in this position. So this is very impressive. So, quite amazing that given just this text, without simulating a board, O3 medium can do incredibly well. But now let's look at this other question. So now let's say I'm playing chess, but I have a new rule. Pawns can capture by jumping forward 5 squares. All right, so this white pawn on A2 could capture a black piece on A7, even if there were other pieces in between. So now, what's a good first move for white under these new rules? All right, so I wish I could give you kind of more time to think about this, but in the interest of time, I'll tell you the right answer, which is you move this pawn forward 1 square, and that's actually checkmate. So the black king has nowhere to go, and that's mate in 1. Human chess players, even without a board in front of them, can sort of get this, right? So you just sort of think about it, and in your mind's eye, you can come up with this move relatively quickly. So how about LLMs? How do they do on this, seemingly much easier question? The answer is not well at all. So this for 2.5 years, this was my favorite question. A new model would come out, I would run and ask this question. I will say, so caveat to this, O3 Pro did get it right once, but if you ask the question from like Black's perspective or tweak it a little bit, it tends to not get it right. So, there's still a gap in understanding there. But, even GPT-5 Pro, very recent model, didn't get it right. So what's going on here? This question is much easier. It's like, and humans can get it. I'll come back. Sorry, is there a question? Yes, go ahead.
Your first example of like how O3 could know like the next move after 8 moves. I'm just wondering, do you think he's thinking about chess, or this is just kind of a usual game that like chess books kind of display, and then like he knows the next move? Or like, do you know if I take like a bigger game where it's kind of clear to us if we move the board, he will be able to reason as well, or is...
So great question. And yeah, no, and I think people have looked at this. I do think eventually, yeah, the sort of state tracking eventually breaks down. And yeah, there was actually a paper from the University of Chicago. This is a few years old now, using earlier models, but actually was looking at the state tracking problem in the setting of chess. So, and actually, I apologize, I don't remember who the authors were, but I'm pretty sure it was from the University of Chicago. But so that's one place to look, or its citations for analysis on this. I do think the state tracking ability is eventually going to break down. So yeah, by the way, I mean, this game is not super duper common. So like if you look in the chess.com database of, I think there are like 3 million master games. I think there are only a couple that actually follow these exact moves. So it's been played before, but it's not like a classical, like very common position. But you're right. I think that is the key difference is that collection of moves, like that particular one may not be super common, but the various moves in it are quite common. And is following the rules of chess, where there's just an enormous amount of data and notation and stuff that's out there on the web. There is no data about this, this new rule that pawns capture by jumping forward 5 squares. So that is, I think, the biggest difference. And in interest of time, I'll sort of skip those details, although I think they're kind of fun. But yeah, this is the lesson. So we see these systems do really amazing things where data is rich. But in analogous settings where humans can perform very well, the systems often exhibit surprising limitations, like in this counterfactual chess example. And so I would speculate that this is going to continue to be a problem for AI for science, because science always, tries to operate at the frontier. It's where there isn't a lot of commentary or evidence already out there, right? It's like we're going out and getting that. That's what science is designed to do. And so I think we're, going to still need to do some work, come up with new approaches to really tackle AI for science because of this issue. Other folks have sort of found similar things in related domains. So open challenge 2, how to build systems with deep scientific understanding. In the remaining couple of minutes, let me go over a couple of other open challenges and I'll conclude. So this paper by Selin and Horvitz plays with the co-pilot analogy for AIs, and it calls out this quote: "Jobs that have a heavy monitoring requirement with little in the way of direct engagement lead to high levels of stress and poor health. And this partly explains why jobs like air traffic control are difficult." So this seems like a bit of a problem for AIs in that the way we're using AI today involves a bunch of monitoring, right? Like they do things and then we check it. It's like, is this right? So this may not be something humans really want to do too much. So an interesting question is, what if we flip this around? And Selin and Horvitz hinted this as well. What if we had the systems do the monitoring? One way to think about that in the context of like a literature summarizer is have the system scour the literature for like new or developments, and then tell us when something that's important to us has changed. So we asked a question before. Now the answer is different because people have done new work. How do we alert users to that? So I think there are tough questions here. When is enough of a change to trigger an update? There's a lot of questions and a lot of papers. How do we do this efficiently? And then how do we communicate to the user just, the new information that they need to learn? So in general, how can we make these assistants into proactive collaborators? And then the last challenge is understanding the user's context. And I talked about this before in the context of evaluation, but I think this is a really important frontier. There's been some work on it, but I think like much more needs to happen. How can we use what we know about the user, their projects, what they already know, what they need to know, in order to give them the right assistance? And so what I'll close with is this graph that kind of plots where I see us today. So I think scientific assistants are useful today. They're very useful. I use them all the time. I use Asta, I use other tools, but they're not great, right? So like for all the reasons I outlined, we still have work to do just to produce, really great answers. So that's kind of the next step. But we don't have to stop there, right? So, think of how far we can push this, like the very best scientific communication. It's like, Neil deGrasse Tyson or Richard Feynman style, like brilliant descriptions of science. So that's what we should be able to get for like every question, right? So like that would be really exciting. And then, finally personalizing this for you. So this, I get really excited when I think about this. Like if we could have systems that tell us exactly what we need to know in like the best way for us in particular, in terms we understand, to understand new science. I think, just to experience this will be really, really exciting. Okay, that was all I had. Talked about Asta, AstaBench, and then these two sub topics within there, and outlined these 4 challenges. Thank you very much for your attention.
Great. Thank Doug. And we have some time for questions. Any question from the audience? I guess I guess like first this is super interesting, and I'm certainly working on a lot of problems in this space. And one thing I'm curious to hear your take is that like there are a lot of challenges in different steps of scientific discovery. Where do you think is most productive to use right now? And where do you think like researchers can focus on to make like actual noticeable progress within like a year or two?
It's a great question, and I think it's complex. So I mean, yeah, the short answer is I'm really not sure. I do think there are settings where there's, sort of like new sources of power, like, using the user context. So like all of your, lab notes, the papers you've written, the papers you've read recently. So using all of that stuff is a little bit of an untapped resource. So I think that's like kind of a good rule of thumb for where there might be big gains to be had, whereas sort of search over large sets of papers has already been done in large measure. So that's one thing I would say. I think for cases where you're talking about experiments and data analysis, I feel like working within computer science has an advantage just because the experiments can be executed at low cost, in software. So that like interface between the experimental apparatus and the agent is relatively seamless. So that's, there are a ton of good reasons to work in like the life sciences as well in terms of the impact of the domain. But in terms of ease of execution, I think, computer science has advantages. So those are a couple of things I would call out, but I think there's like room to improve. Like that was one of the things we saw with AstaBench is like everywhere you look, there's headroom. So I think, choosing what you're most passionate about within this like wheel, and going for it is, I think relatively likely to bear fruit.
Cool. We're technically time. Maybe we'll take one more questions, but if you have other questions, feel free to post on Discord or you can email Doug. And I guess like it'll be great to make Discord a more lively discussion outside of the talk session as well. The question, I'm just going with time with order here. The question is, how do these results vary by domain? For example, CS versus social science?
Yeah, so great question. I can say we get a whole bunch of social science queries in our summarized literature tool. So it's at least getting a lot of use. We don't have things like an accuracy measure broken out across different fields. In fact, our summarized literature benchmark is just computer science. So yeah, so there's more work we need to do there to really understand how we vary across field. The one thing I would say is we get actually a very large number of social science queries. I think I saw more than 100,000 of our queries are broadly in the social sciences. So, seems like those users are engaged, but we don't have great measurements. It's a good question.
Great. Thank you so much. In the interest of time, we'll end here, but hopefully like this conversation goes beyond this. And I personally think this is a very exciting area that we are doing this series of seminars. Please let your friends know if they would find this interesting. We are going to keep doing this for 4 more talks this quarter. And in the winter, we are putting together another lineup of speakers, which we are also very excited about. All right, see you guys. Thank you for joining.
Thanks very much, everyone. Take care.